okay? And so it is basically a nonpolar bond. Everything else, when there are two dissimilar elements, they are a polar bond. And then we looked at the electronegativity of those two elements that are bonded and determined which one is more electronegative so that we can write the arrow. Remember the arrow? And chloride here is a lot more electronegative. And so we drew the arrow going from hydrogen to chloride, which told us that on the chloride side, we call that symbol partial, that's supposed to be a negative, partial positive on the hydrogen side, and I got to erase that. Partial negative on the hydrogen side, and a partial positive on the hydrogen side. So the chloride had the partial negative, and the hydrogen had a partial positive. That is what we call a dipole bond, okay? Now, with respect to ionic compounds, there's no dipole there. There's simply a full-fledged negative or positive on there. And those are examples where we had a metal and a non-metal bonded together, okay? So refresh your memory about electronegativity. Whoa. So if we look at, thousands of these molecules interacting with each other, then we are looking at the intermolecular forces denoted by that blue dotted line and how they react with each other. And you're familiar with a lot of things right now. There's certain things like, heavy lard butter that's solid compared to liquid butter. So, okay, those intermolecular forces of the molecules of the heavy, thick butter are very strong. Hence, they have a solid property. The ones that are softer, like say vegetable oil, they're liquid. Those intermolecular forces are much less. Okay. So there's only 4 types of intermolecular forces. Okay. And these are the interactions, I repeat, the interactions between the partial positive and the partial negative of the molecule. Okay. There's only 4. The first type is called London dispersion forces. This is the easiest one to remember. Those are those molecules that are non-polar. So all the diatomic molecules that we talked about before have no fear of ice cold beverage. Their only force they have is London forces, London dispersion forces. And the other one, so everything that is diatomic, there's an area I can't write on. Everything is diatomic, okay, and the carbon-hydrogen bond, okay? Those compounds, the only force they have are London dispersion forces. The other second type is called a dipole forces, or DDF, okay? In the previous slide, you saw the example of hydrochloric acid interacting with another molecule of hydrochloric acid. That's when we have 2 dipoles interacting with each other, okay? Those are called dipole forces. They're a little bit stronger than the London dispersion forces, just a little bit. And finally, we have number 3, which we call hydrogen bridging. You also will see the name hydrogen bonding. Okay, so there you'll see the name hydrogen bridging or hydrogen bonding. They're both the same. Okay, they're trying to use a new naming for bridging for this particular force, but the rest of the world is still using hydrogen bonding forces. Then finally, number 4, it deals with interactions between an ion and a dipole forces. The majority of the time, we're looking at aqueous systems for number 4, water solutions, okay? And so looking at the questions asked when they talk about sodium chloride in water, the only interaction that's occurring there is number 4, the ion dipole. The dipole comes from the water, and the ion comes, well, from whatever salt ionic compound you're working with. Okay. All right. So we're going to go through some examples of these forces. Okay. The first example, as we talked about, number 1, are London dispersion forces. These are temporary forces. They're not very strong. And the important part to remember is only the non-polar bonds molecules have them. If you have non-polar bonds all around your molecule, you're going to have non-polar molecule. Refresh your memory on that exercise we did in the previous chapter. Okay. Now, what's happening here, the electrons from one compound are actually pushing the electrons from another species, another compound. And it forces those electrons to create a partial negative and a partial positive side. Okay. We will have, oh, what happened here? I was going the wrong way. Okay. So they're not very close together, and they're far apart. So gases have a lot of London forces involved, and they're pretty weak. And how they work, in the next slide we'll show you how that works. But keep in mind, when we're dealing with molecules that are non-polar, they have just London forces to deal with. And the bigger the molecule, the stronger or the more London forces you have. So if I'm comparing something like fluorine versus, say, bromine, both of them are nonpolar, the guy taught me, but the interactions with bromine will be much stronger simply because that molecule is much bigger than fluorine. Okay, and the way that occurs is you can see here, and you've probably done this yourself. If you ever, think about this for a second, a little side note, how to explain these London forces and how they work. Next time you got a balloon, and I was looking for one here, but I don't have one. You take that balloon and you rub it on your head, and what you're doing is you're transferring the electrons to the surface of that balloon. Then you take that balloon and you put it on your body someplace, your chest, and it sticks. You often wonder why it sticks. Well, think about it for a moment. That balloon is full of electrons that have negative charge. On your body, on your chest, you also have electrons, okay? So as you bring those electrons on the balloon closer to your chest, you cause those electrons on your body to go away from the surface, creating a more positive charged area. And so that balloon sticks to your chest for a short period of time, like a magnet. Eventually the balloon falls apart and, falls off. And, it doesn't stick there all day. That's because the London forces, dispersion forces, are fairly weak. And that's what's happening here. Okay? As the molecules come together, two nonpolar molecules come together, the electrons end up, from one of them, pushes the electrons away from another molecule to create a temporary partial positive and a partial negative on the molecules, and therefore the interaction. There is a subtle interaction occurring between the molecules right there, okay? And obviously, if these molecules are bigger, like the last slide, if it was a big giant dipole molecule reacting with another gigantic one, because there's more electrons, those forces will be a little bit much stronger than the one that's smaller. Okay. So that's how those work. All right. Now, with respect to dipole-dipole forces, that requires that the bond of a molecule is polar, two dissimilar atoms, and one of them has a lot more electronegative than the other, so we create that permanent dipole. In the previous example, that dipole was only temporary, okay? Just caused by the movement of the electrons. When we're dealing with dipole-dipole forces, those are permanent dipoles, okay? In that example we did with HCl, hydrochloric acid, that has a permanent dipole. Oh, they didn't come out here on my screen. Let me write that over here to my left. Okay? Because the chloride in that example is a lot more electronegative than the hydrogen. So that dipole remains, it's always there. So for these forces, we are dealing with polar molecules only. Okay? And essentially, they line up with each other because of the property that each molecule has. Notice in this example, we have a very large hydrochloric acid, a very large partial negative, interacting with the partial positive of another molecule, giving us this interaction there, okay? This attraction. Opposites attract. There's going to be an attraction there, okay? And the strength of that interaction determines such physical properties like boiling point, surface tension, and so forth that we're going to talk about here in a bit. Okay, so here's again, these are much stronger than London forces, and the molecules must be polar, okay, permanently polar molecules. All right, which brings us to hydrogen bridging, and I put a parenthesis bonding because that's also, this force is called that, bonding or hydrogen bonding, okay? Now, these molecules also have a dipole. They have a permanent dipole, okay? But these only apply to three types specifically. And if you can see up here, NOF, okay, otherwise not on file, for example, when a nitrogen and an oxygen and the fluoride are bonded to a hydrogen, as I underline those, yes, they have a dipole, but because of the particular property of hydrogen bridging, it only applies to those atoms, nitrogen, oxygen, and fluoride, when they are bonded to a hydrogen. And this bonding is very, very strong, okay? Water, for example, boils at 100 degrees Celsius. That's a lot of energy to get that thing to boil 1 atmosphere, because it has to break up that interaction that's occurring between the molecules. And here it's a very strong hydrogen bridging or hydrogen bond that's occurring there. Okay. They try not to use the term hydrogen bond because it gives the impression that we're actually physically attached. And that's why they want to go through a bridging naming instead of bonding. But it's an interaction that's occurring between the partial negative of the oxygen and the partial positive of the hydrogen. And that interaction, if it's very strong, has a big factor in the physical properties of that molecule. Okay. So to kind of summarize this part, hydrogen bridging, you must have nitrogen, oxygen, and fluoride bonded to hydrogen. Otherwise, everything else is just a dipole when it comes to polar molecules. Okay. This is again another diagram that talks about the hydrogen bridging. Okay. It's much stronger than a dipole, but it is weaker than the actual bond itself. Okay, these forces that we talked about, they're strong, but when it comes to the bond itself or the interaction of covalent and ionic bonds, they're much, much weaker. But they have a big effect on the physical properties of these molecules. Okay. Finally, the last example, which is called ion dipole forces, that only applies to ions, ionic compounds. In that picture you can see there, you got sodium ion that is dissolved in water, completely interacting with the water molecules. Okay? And because sodium ion has a positive charge and water is very dipole, and then so the partial negatives of the oxygen are interacting with the positive charge of the sodium. That means if this was sodium chloride, the anion would be out here on the side here interacting with the partial positive of the hydrogens of water. So it's a very complex picture when it comes to ion dipole interactions. Okay, and they're very strong. When you boil these, you're not going to cause the sodium to evaporate. In fact, the water evaporate even behind the sodium salt. Okay. Now, let's kind of summarize the difference. When we talk about the bonds, okay, not to confuse the two, when we talk about the bonds, we're talking about either a ionic bond, okay, and refresh your memory about ionic bonds. That is a bond between a metal and a nonmetal together, okay? And covalent bonds deal with bonds that are nonmetals, two nonmetals. They differ in that you're either going to have equal sharing or not equal sharing. If you have non-equal sharing because of electronegativity, in other words, two different atoms, you end up with a polar covalent bond, okay? So it's unequal sharing involved there, creating a partial positive and a partial negative side for that particular compound. Then we have the covalent bonds that had equal sharing of that bond, of those electrons in that bond. And those are nonpolar, okay? All of the diatomic compounds are nonpolar because the two atoms are the same. There's an equal sharing of the electrons in that bond. And then we added the other example with carbon hydrogen, okay? And simply, even though they're different elements, their electronegativity to each other is minuscule. There's literally no difference, therefore they're nonpolar, okay? So not to confuse the bonds with respect to the forces. The forces, when you have nonpolar molecules, the only force you have between molecules is the London dispersion forces. When you have polar molecules, okay, then you're dealing with dipole forces. And only when you're dealing with hydrogen bonded to nitrogen, oxygen, or fluoride, that you have hydrogen bridging / bonding, okay? So yes, they do have dipole, but they have one more force that's even stronger than the dipole. And then finally, the ion dipole forces deals when you have a particular ion interacting with a polar molecule. And 99% of the time, you're dealing with water. Water is obviously very polar, okay? And so you're dealing with an aqueous system and some salt dissolved in the aqueous system. Okay, now, you might see a table that looks like this. And you need to figure out, okay, what is the strongest intermolecular forces on the right column? Well, to answer that, this is where the Lewis dot structures come into play. Way back when we were writing these, that's why we wrote these Lewis dot structures, because from that information, it told us if we have a polar molecule or a nonpolar molecule. So go back and review review the Lewis dot structures, because we did carbon dioxide. Now, carbon dioxide, we got carbon and oxygen, but we would say, okay, I got two dissimilar compounds, two dissimilar elements bonded. I must have a polar compound. But remember that once we went through the Lewis dot structure, we found that carbon was double bonded on each side with oxygen. Okay. And yes, we had a dipole that went from carbon to oxygen, but they went in opposite direction and therefore canceled the dipole of the bond, which made it a nonpolar species. Okay. All right. So come on. So carbon dioxide is nonpolar, and then automatically, since it's nonpolar, the only force you deal with is the London forces. Okay. The PF3, again, we have to draw the structure, the Lewis dot structure, and when we do that, you will come up with phosphorus in the center and the 3 fluorides bonded to it. But furthermore, you will find 2 lone pairs of electrons on the phosphorus. And recall what I said about lone pairs on the central atom. The moment you get that, automatically polar molecule, okay? Or 1 lone pair or 2 lone pair, like water has 2 lone pair. Water is very, very polar, okay? So that being the case, PF3 phosphorus trifluoride is polar. Next thing you ask, there's no hydrogen involved here. It's just fluoride and phosphorus. So there's nothing to do with hydrogen bridging. So the only option you have is dipole-dipole, okay? Obviously, it's not London because it's polar. It's not ion dipole because there's no mention of an aqueous solution here or ionic compound. And so you have to decide which one is a dipole-dipole or hydrogen bridging. Well, you can eliminate hydrogen bridging because there's no hydrogen involved with either nitrogen, oxygen, or fluoride. So it's the only thing involved here is a dipole-dipole. HF, okay? HF, very polar species, okay? Very polar species, just like chloride. Hold on, I gotta let that one more in. All right. HF, just like HCl, is a very polar species compound. Okay. So obviously not London, obviously not ion dipole. You have to decide, is it dipole-dipole, hydrogen bridging? Remember, NOF. We have here in this example, fluoride with hydrogen. So the force interaction here is hydrogen bridging or hydrogen bonding forces. Okay. Now, the fourth one is all you see here is carbon and hydrogen. That's all you see, carbon and hydrogen. Okay. Automatically, remember a carbon-hydrogen bond, nonpolar bond. I got 4 of them around there. I'm going to have a nonpolar compound. All hydrocarbons are nonpolar. Okay. Having a nonpolar, the only force involved here is London forces. Okay. And finally, the last one, where you see that you have Ki, potassium iodide, that should tell you, okay, I'm dealing with the ion. I have an ionic compound in water because the state is AQ, aqueous, right? So it has the only force involved there is the ion dipole. Okay. Let me summarize here. So to determine what force a molecule has, you have to first determine whether it's polar or nonpolar. Okay. And if it's nonpolar, then London forces. If it is polar, then you have to decide, okay, do I have hydrogen bonded to either nitrogen, oxygen, or fluoride? And if you do not have that scenario, then it's dipole-dipole. If you do have that scenario, then it's hydrogen bonding or hydrogen bridging force, okay? And with respect to the last one, the moment you see an ionic compound with the state of aqueous, automatically ion dipole interaction. Okay. Now, basically here, there's a law called Coulombs Law, and the really the only thing that we need to take away from this is to say, when we look at the interaction between charges, okay, which also applies in this example, they're using two magnets, but the forces interacting in the molecules is very similar, okay? And so what they're saying here is the attraction between two charges is proportional to the magnitude of the charge. It makes sense. Think about it. The stronger the charge, the stronger the force or the attraction. And then they're telling you that it's inversely proportional to the distance. Well, all that means is that, when something is directly proportional, if I change a variable, then B changes the same amount, okay? There's a direct relationship. Inversely proportional just says if I change A, then B drops, okay? And if you think about it for a moment, I'm sure you've done it before when playing with magnets or working with magnets. If I get two magnets and I bring them together, but don't let them completely attach, but really hold them apart, you can feel that force of attraction. Or you can put two magnets with the north sides coming together, and you can feel that force trying to repel it. Okay. As you move away one magnet, the force is still there, but is not as strong. Okay, not as strong. And this is basically what it's telling you. And that equation that pops up is normally I would go through some examples on the board, but mathematically what it says that if Q1 and Q2, if I increase that magnitude, that charge, my total force would increase. K is a constant, it stays the same. So if I increase the charge of Q1 and Q2, my total force increases, okay? R represents the distance between them. And if you think about it, if I start off with a distance of say 1 centimeter, I have an X amount of force because 1 centimeter squared is 1, okay? But let's double that 1 centimeter to 2 centimeters. So now 2 squared is 4. By increasing that distance, I decrease my force by a factor of 1/4, okay? 1/4, so it's basically what this whole thing's all about. Directly proportional to the charge, inversely proportional to the square of the distance between the charge. All right, so we have a table here, and they want you to choose whether the forces that are being asked are the forces of the bond, which means the type of bond that it has, or is it the IMF forces? And some of these questions could be tricky, so you got to read them carefully. For example, if you read the first one, it says, what holds the atoms together in one ammonia molecule, NH3? We're talking about one ammonia molecule and what is holding the atoms together. And so we're not dealing with other molecules of ammonia, just one. And so we're dealing with a bond. And so in this case, we're dealing with a phosphorus nitrogen hydrogen bond, which is a polar covalent bond. Okay? So we're talking about just the molecule itself. Now, second question says, what is holding the sodium ions in water? Well, the fact that you are dealing with sodium ions and water, there's only one force involved there. That's the ion dipole force. Okay? Number 3, what is holding 3 hydrochloric acid, HCl molecules together? Now we're looking at IMF forces. okay? IMF forces, because we're talking about 3 molecules of HCl. So now you have to decide, is HCl polar? Very much so. It is polar, so therefore London forces are not involved. Now you have to decide, is it dipole or hydrogen bridging? Well, it can't be hydrogen bridging. Why? Because hydrogen bridging only involves nitrogen, oxygen, and fluoride. Here we have chloride. So the only force that's involved here is simply the dipole-dipole forces, okay? Next question, what is holding the ions together in salt, sodium chloride? No mention of water, it's just asking you, I got solid salt. Okay, so they're asking you, what type of bond is sodium chloride involved with? And those are simply ionic bonds. Okay. Okay. Question here, what is holding 4 H2O molecules together? Now we're dealing with other molecules of water, so we're dealing with IMF forces. Okay. H2O is definitely always polar. Just put that in long-term memory. Okay, so being polar, is it dipole-dipole or hydrogen bridge? Well, in this case, we have hydrogen interacting with oxygen, which is part of the 3, NOF. So therefore, the forces involved here are hydrogen bridging. Okay. Now, next question. What holds nitrogen gas molecules to each other? Recognize they're talking about nitrogen gas is part of the diatomic molecules, nitrogen. And 2, it is nonpolar because all diatomic molecules are nonpolar. Therefore, the only choice you have here is London forces, okay? What is holding the oxygens together in an oxygen gas molecule? All right, so question is, what is holding the oxygens together in one oxygen gas molecule? Again, here we're dealing with 1, therefore we're dealing with the bond, okay? And O2 is nonpolar. So it's a nonpolar covalent bond, okay? And finally, the last one, what is holding 2 ammonia molecules together? So again, we're dealing with other molecules of ammonia, okay? And so we need to remember the formula for ammonia, which is NH3. We use that a number of times, okay? We also know that it is polar, so polar covalent. So it's either dipole or hydrogen bridging. It's hydrogen bridging here because it is part of the NOF, nitrogen and hydrogen. Therefore, we have hydrogen bridging / bonding forces holding 2 ammonia molecules together. Okay, and so when you see these questions, when you read them, you got to decipher, are they talking about a particular molecule? And if they are talking about a particular molecule, we're talking about what type of bond. If they introduce more molecules, then we're talking about IMF interactions, and then determine which one of the 4 are those IMF interactions that are occurring here. Okay, this kind of flow chart kind of helps you out. Okay, so obviously if it's covalent, if it's ionic compound, then it's going to be an aqueous system, and you have ion dipole. So if it's covalent, if it's nonpolar, automatically London forces. Okay, if it is polar, you have to decide, well, could it be dipole-dipole or hydrogen bridging? If it's involved with nitrogen, oxygen, and fluoride, hydrogen bridging. If it's not, then it's dipole. Okay, and of course, if it's polar, it's ionic. And so if you got water involved, then it's the last choice. Now, how do these affect some physical properties? How do the IMF interactions affect the physical properties? Now, we're going to look at 4 physical properties: paper pressure, boiling point, surface tension, and viscosity. Normally in class, y'all remember I will always take my soda pop. I don't know why my video's off. Okay. For some reason, my video is off. Okay, give me 1 second. Well, I'm assuming you guys can see the slides okay because I'm running that off my cell phone. Yes, okay. Aren't you seeing? Okay, as long as you're seeing the slides, that's fine. I'm assuming you can hear me because I see my microphone goes up and down. But for some reason, my video. What I was going to demonstrate with respect to vapor pressure, I'm sure you've had a kind of half-empty bottle of soda pop. Okay, so you got the liquid in the bottom half of your container, and then on the surface, and it's capped. And then in that area where the air is, if I were to put a pressure gauge in the side, I could measure that pressure. That is the pressure of the gas coming from the soda pop that is in the empty space, and that is what we call vapor pressure. Okay. Now think about this for a second. When the IMF interactions are strong with the molecules in the liquid, that vapor pressure is going to be much less. Okay. Why? Because the molecules hold on to each other stronger. Therefore, less liquid goes into the vapor. The converse is also true. If the interactions are weak in the liquid phase, then more of these are going to go, more of those molecules are going to go into the gas phase. Okay, so our vapor pressure goes up. Think about that. All right, boiling point. That is the temperature in which a liquid boils. Water, for example, boils at 100 degrees Celsius. Okay, things like alcohol, for example, ethanol boils at about 78 degrees Celsius. Okay, so the fact that it boils much less infers that the interactions of ethanol are much less than the IMF interactions of water, because it doesn't take much energy to break apart those interactions, the IMF, to get it going to the vapor phase as compared to water. Okay, surface tension, similar scenario. We all know that, if you ever take your car out and get it waxed, you add water to it, it bubbles up, right? That's surface tension. If the surface of your car is pretty dirty, when you throw some water in it, the water kind of flattens out, okay? Well, IMF interactions affect that. If the molecules are held on very tightly because of the IMF forces, then that bubble will be greater as compared to those liquids that their IMF interactions are less, and that bubble will be much flatter. I have some examples here to show you in the next few slides. Viscosity, basically a measurement of how thick something is, okay? If I were to take a cup of water and a cup of honey and I empty them, obviously the water is going to empty much quicker than the honey, and the honey flows much slower. So that infers that the IMF interactions of honey are much stronger than the ones of water. That's why it flows, it's thicker. Now, what do I do to make that honey run a little quicker? We heat it up. And guess what? When you heat up that honey, it runs quicker because you're breaking up these IMF interactions, okay, and causing the molecules of the honey to be further apart, breaking up those interactions. Okay, so vapor pressure, excuse me. Again, it's just the amount of pressure of the liquid going into the vapor phase. Okay, that's all it is. And obviously, the stronger the forces are in the liquid, the stronger they are, the less molecules go into the vapor phase. All right. Now, eventually, if you didn't have a cap container, all the liquid will evaporate. Okay. Case in point, your soda pop. Uncap it, leave it on your bench top, on your tabletop for a couple hours. It loses its fizz because all that carbon dioxide eventually escaped. Right? Right. So, vapor pressure, all that is just the amount of pressure exerted of gas molecules in the closed container. So, stronger IMF interactions, you are going to have lower vapor pressures. Why? Because the liquids, when it's in the liquid, because those forces are strong, less molecules in the liquid will go or escape into the vapor, okay, because they're being held on much tighter, okay? A good example is here. You can see they're asking here, which has a higher IMF? Well, A has a higher IMF, a weaker IMF, excuse me, simply because the interactions down in the liquid phase are weak, causing more of the molecules to go into the vapor phase, okay? Therefore, it would have a higher pressure, vapor pressure, because there's more gas molecules in the gas phase. On the right, the fact that there's less molecules in the gas phase tells us that these interactions compared to A are much stronger and less molecules go into the gas phase. Okay. Boiling point, that is the temperature which liquids change to gases. Okay, so strong IMF will have a higher boiling point because it's going to take a lot more energy to break up those interactions, to break them up, to get them into the gas phase. Water, I use that example a lot, boils at 100 degrees temperature. That's very, 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 fairly high, right? Good example would be fingernail polish remover. Very volatile. You open the cap and you smell that acetone just evaporate, you know, because the interactions of the acetone in the bottle are weaker, and so a lot of them go into the gas phase very readily. Okay, surface tension, again, strong IMFs gives us high surface tension, okay, because they attract each other much stronger. So the result being, if we look at a diagram of two liquids, A and B, we can infer that A has a higher IMF, okay, because it's holding on to its molecules much tighter and stronger, and it's kind of making that bubble compared to B, where the interaction is much less. Therefore, on the surface, a drop of it will just spread out. Viscosity, we all know that oil flows, honey flows slowly, has a high viscosity. Okay, things like vodka liquid, low viscosity. Okay, and so stronger, if you have a strong IMF, would your viscosity be higher or lower? Okay, it's going to be higher because molecules are held together much stronger. So honey has a much higher IMF interaction than, say, other liquid like water. Okay, When we do comparisons here, we can't really give absolute values. All we have the ability to do is to give you relative answers. So we're always going to be comparing two molecules, and then from that determine which one will boil higher, which one will boil lower, which has a greater viscosity, things like that. Okay. So, for example, here, they're asking you, let's compare ammonia with fluorine and what EMF do they have? Well, before we can compare anything, you got to refresh your memory. Ammonia, we just did this a number of times, has that formula, NH3, with lone pair. And then fluorine is part of the have no fear of ice cold beverage, it's diatomic. So before we do determine whether it's polar or non-polar, we have to write the formula, know the formula. Ammonia on the left is polar, okay? Fluorine on the right is non-polar, okay? Not only that, ammonia, we have hydrogen and nitrogen interaction, so we're talking about hydrogen bridging. So we have to determine first polarity and then what type of force we're dealing with. Obviously, we got to write the formulas and then determine the force involved for that molecule. So hydrogen bridging for ammonia and London forces. And then recall of those four forces, which is the weakest one. In this case, London forces is the weakest one. Okay. So question number one, which has the stronger IMF? Okay, well, we just determined ammonia has hydrogen bridging forces, which is the strongest of the forces. So ammonia has a stronger IMF. Which has the lower boiling point? That would be the one with the weaker IMF, which would be fluorine, because it has London forces, the weakest of the four. Which one is polar? Well, we know fluorine is diatomic, non-polar. Going through the Lewis dot structures, ammonia is very, very polar. Okay, so ammonia is the polar guy, which has a higher vapor pressure. To have the higher vapor pressure, you have to have the weaker IMF. And in this case, fluorine having London forces, the weaker one, would have the higher vapor pressure. And then which one would be the least viscous if they were in the liquid phase? Okay, so the one with the weakest IMF would be the least viscous. It's fluorine in this case. And which has the more surface tension? Again, here, ammonia will. Ammonia would beat up much more than the fluorine if both are in the liquid phase. Okay, so filling in the blanks. If we increase the IMF, viscosity goes up. If we increase IMF, the boiling point goes up and the surface tension goes up. Okay, and so again, by increasing the IMF, we increase the interactions between the molecules. So that means viscosity, boiling point, surface tension goes up, which means that less liquid will go into the gas phase and therefore its vapor pressure drops. Okay. So here the question was if as IMF increases, so on and so forth. But the question could be as IMF decreases, what's the result? Okay. So try to answer the question if it said decrease rather than increase, would be the opposite. Right? Just a quick note about water and this structure. Water is the most polar liquid out there. Okay. We know through the Lewis dot structures that we've done before, it has two lone pairs and two bonded pairs. we know that the bond angle between them is much less than the standard reference 109.5 because of the lone pair. And the result is it's very, very polar liquid. Can dissolve many compounds, mostly ionic, but it can also dissolve a lot of covalent or non-ionic compounds. Okay, and there's a very strong force, the hydrogen bridging force between molecules. Now, properties of water: very polar, very high IMF, low vapor pressure, usually a high boiling point or melting point. We got 100 degrees and 0 degrees Celsius. Has a high surface tension. And something interesting about water that doesn't occur with a lot of molecules is that on freezing, it actually expands. Okay, and which is kind of interesting for that molecule. And it also flows because its density changes, becomes less than 1 in liquid water. Okay, and causes frozen water to float while it's in water. Okay, and as it expands, those who've ever lived in cold areas, your water pipes can burst, and cause all kinds of problems because of the freezing of water. One of the reasons that happens is when it freezes, water molecules form these very organized and specific structures. And it's interesting how Mother Nature picks the six-member ring, the hexagon shape. Okay. All right. So we're getting close here. The heating curve about water. And this is true for a lot of compounds, and it's related to the IMF interactions. But if we were to take, in this case, we're going to use a liquid, in general example, a liquid. Obviously, we have a graph here of temperature versus the amount of heat given. So we start off at some point, everything's in the solid form. Well, as we add heat to it, our temperature goes up. Okay, well, we get an incline right here, and all that material is melting. Okay, then what happens when we reach the melting point? Basically, as we go up the hill, everything's in the solid form. Now, when we reach that particular temperature, when that solid begins to melt, we actually hit a plateau. And we continue to add heat, okay, we have a plateau. At that plateau, we have a mixture of solid and some of it going to liquid, okay? Then eventually, when all that solid has melted and now becomes liquid, we got another jump increase in temperature as we add more heat. Here, it's all in the liquid phase. And guess what? We hit a second plateau. Okay, and it could be whatever temperature this liquid starts to boil. What is happening at each plateau, all the energy you put into the system at this plateau and in that plateau, what you're doing is you're breaking up the IMF interactions between the molecules. You're breaking up the IMF interactions, and hence we have a plateau. Okay, until such time, in each plateau, the first one we have a mixture of solid and liquid, and the second plateau we have a mixture of liquid and gas, until all of that liquid has now been converted to the gas phase, and we have another increase in temperature. Okay, but at the plateaus we are breaking up those interactions. Okay, this is what happens. In this example, we're looking at water. This could be a very good example of water. And so this could be 100 degrees Celsius, and this one down here would be at 0 degrees, okay, Celsius. And so we hit two plateaus. Well, notice here, big plateau. We have a mixture of liquid and gas. First plateau, a mixture of solid and liquid. So if you're ever boiling water and you hit 100 degrees, and you think, well, maybe I'm going to add more heat to it, save your money because you're not increasing the temperature at all. You're going to stay at that plateau as long as you got liquid in there. Okay. So, but at the plateaus, what is happening, all that energy that you add into the system is breaking up the intermolecular forces of the molecule. Okay, so the phase changes, the temperature stays constant. At the phase change, all the energy goes into breaking up the molecule. Okay, and then you're either, depending on which direction going in the curve, left or right, you're either breaking up the interactions or forming new IMF interactions, either direction. Okay, that's a nutshell. And guess what? Rose and Tiffany are the only two that remained. We have finished chapter 14. Okay, so pretty short. On Tuesday, we will go through chapter 15, and that's probably, I believe, 12 slides or something like that. So we'll be done with all the chapters on Tuesday for sure. And then we can do review starting then, or Thursday for sure we'll do some review. Okay. So any questions? No questions? Okay. Well, Rose and Tiffany, thank you for showing up. Appreciate it. We'll see you guys. Yeah, review next Thursday sounds good. Yep, it will. We'll make review next Thursday, maybe even Tuesday, because like I said, I think 12, 13 slides. That's pretty quick. Okay, you guys take care. We'll see you Thursday. Don't forget my office hours there if you need more help. You guys take care. Bye-bye.